Week 2, Lesson 6, Fatigue Fundamentals. Static failure asked whether one application of a load breaks or yields a part. Fatigue asks a harder question. Will a load far below yield eventually crack the part because it cycles thousands or millions of times? This lesson builds the endurance limit, the stress a steel part survives essentially forever. Then knocks the ideal lab value down to a real part with the 5 Marin modifying factors, and reads it all off the SN curve. It opens a 2-lesson fatigue pair. Here's the problem. A machined steel shaft spins in rotating bending, room temperature, nothing special going on at the surface. You're given its ultimate strength and its diameter. Find the modified endurance limit, the stress below which this real part lives forever. The catch: the textbook endurance limit is a polished lab value. This shaft is rougher, thicker, and loaded its own way, so we scale that ideal down with 5 factors. Concept 1. Fatigue fails below the static strength. A load too small to break or yield a part in one shot can still crack it if it cycles enough. For steel, there's a threshold. Below the endurance limit, the part survives past about 1,000,000 cycles, essentially forever. Above it, life is finite, and the part eventually fails. That flat threshold, the knee in the curve, is special to steels. Non-ferrous metals never truly level off. Concept 2. The SN curve has 2 regions. The sloped part is finite life. A power law relates the fatigue strength to the number of cycles, with a slope and intercept fit from 2 known points. Follow it down, and it bends at the knee into a flat horizontal line, the infinite life region. Any stress at or below that flat line, and the part never fails by fatigue. So the entire job comes down to one number. Where does the flat line sit? Concept 3. The ideal limit and 5 knockdowns. For steel with no test data, the rotating beam endurance limit is simply half the ultimate strength, capped once the ultimate passes 1400 megapascals, where it holds flat. But that's a polished lab specimen. A real part is rougher, larger, and loaded its own way, so we multiply that ideal by 5 Marin modifying factors: surface, size, load, temperature, and miscellaneous, to get the true endurance limit. Setup Part 1. The surface factor. A rougher finish nucleates cracks earlier, so the surface factor falls as the ultimate strength rises. Pick the row for your finish, and read a coefficient and an exponent. The one trap: the table lists the coefficient in 2 unit systems, KSI and megapascals. Our strength is in megapascals, so we read the megapascals column. Setup Part 2. The remaining 4 factors. Size. For bending or torsion, a mid-range diameter uses a power law that shrinks the limit as the part grows. But for axial loading, size drops out entirely and the factor is 1. Load type: bending is 1, torsion about 0.58, axial about 0.92, temperature is 1 up to 450 Celsius, and the miscellaneous factor is 1 unless corrosion, plating, or residual stress is called out. For our shaft, bending, 30 millimeters, room temperature, nothing special, only size and surface bite. Solve Part 1. The ideal limit and the 2 factors that actually move. The ultimate is below the cap, so the rotating beam limit is half of it. The machine surface factor comes from the table's megapascals row and lands near 0.83. The size factor for a 30mm shaft in bending comes from the power law, about 0.86. The load, temperature, and miscellaneous factors are all 1. Bending, room temperature, nothing special. Solve Part 2. The cascade. Multiply the ideal limit by all 5 factors. Only surface and size are below 1, and together they cut the limit to about 70% of the ideal. The modified endurance limit comes out near 212 megapascal. That's the number you designed to. The real parts survive forever stress. The raw lab value of 300 would badly overstate what this shaft can take. Traps. 5 ways the fatigue setup bites. 1. Quoting the polished lab value for a real part. Always derate to the modified limit. 2. Forgetting the cap. Half the ultimate only holds up to 1400 megapascals. Then it's a flat 700. 3. Grabbing the wrong surface coefficient. megapascals strength, megapascals column. 4. Applying a size knockdown to an axial part, where the size factor is just 1. 5. The wrong load factor. Bending, axial, and torsion each have their own value, and a mismatch throws off the whole limit. Quick recall. Start from the ideal limit, half the ultimate, capped at 1400 megapascals. Multiply by the 5 Marin factors: surface from the table's megapascals column, size from the bending power law, load by type, temperature, and miscellaneous, usually 1. That product is the modified endurance limit, the flat line of the SN curve, and the stress you design a real part to. The sloped finite lifeline uses the power law when the stress sits above the limit. Next up, Lesson 7, Modified Goodman and Soderberg. This lesson built the endurance limit for fully reversed loading, but real parts usually carry a steady mean stress with an alternating stress on top. Lesson 7 combines those two against the endurance limit you just found, using the Goodman and Soderberg criteria to produce a fatigue factor of safety. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.